The most useful tool for a chemist is the periodic table. In the periodic table, we have all of the elements arranged in a very particular way, and we can extract lots and lots of information about the different elements known to man. So it's important that we understand how we can read this table and extract the information that we need from it. First, let's familiarize ourselves with some of the basic information that's given in each square on the periodic table. The periodic table consists of a number of squares. Each square contains information about a given element. So if we take, for example, carbon, we'll notice that the symbol for the element is in the middle of the square. Then we will have the atomic number somewhere in this square. Sometimes it's up in the upper left-hand corner, sometimes it's up in the upper right-hand corner, sometimes it's in the middle of the top. Typically it'll be someplace along the top of the square. So for carbon, the atomic number is 6, so we're going to see a number 6 somewhere in that square. Then we're also going to have the average mass of a carbon atom someplace in this square. So the average mass of a carbon atom is 12.011 AMU. These are the three basic things that are in every periodic table in each square. Sometimes periodic tables will give more information than this, and you'll see other things in the square, but this is the basic set of information that every square has. Here is an example of a typical periodic table. Notice that the elements are arranged in order of their atomic number, or the number of protons in their nucleus, which will equal the number of electrons in the neutral atom. So we start with 1, hydrogen, 2, helium, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so forth and so on. In addition, there are rows and there are columns. The rows tell us something about where the electrons are in the atom. So in this first row, the electrons for the elements in that first row exist in the first shell closest to the nucleus. Remember that we said that that first shell can hold up to 2 electrons. And so hydrogen, which when it's neutral has 1 electron in that shell closest to the nucleus. Helium, which has 2 electrons in its neutral state, has 2 electrons in the shell closest to the nucleus. That's all the electrons that that shell can hold. So when we go to lithium, which has 3 electrons, we have to start putting electrons in the second shell, and so lithium starts the second row of elements. So each of these rows tells us about the shell where the electrons are held. So this is in the first shell, this is in the second shell, this is in the third shell, this is in the fourth shell, this is the 5th shell, this row is the 6th shell, and this row fills the 7th shell. The columns, on the other hand, tell us the number of electrons in the outermost shell. So for instance, lithium, which has 3 electrons, has 2 electrons in the innermost shell and 1 electron in the second shell. So it's in column 1 because there's 1 electron in the outermost shell for lithium. However, sodium has 11 electrons, so there's 2 electrons in the innermost shell. There are 8 electrons in the second shell. That's a total of 10, plus 1 electron in the third shell. Sodium is in the third row because its outermost electron is in the third shell, and it has 1 electron in that third shell, so it is in the first column. Things get a little bit complicated past the third row, but when you learn all the rules for how electrons are distributed about the nucleus, you'll find that potassium, with its 19 electrons, has 1 electron, because it's in column 1, in the 4th shell. There are several different ways to name the columns. So the older numbering system uses 1A, 2A, and then we have a bunch of B-type columns. and then 3A, 4A, 5A, 6A, 7A. If we use that numbering system, then the number of the column refers to the number of electrons in the outermost shell. If we just number the columns 1, 2, 3, 4, 5, 6, 7, and so forth and so on, which is the newer numbering system, then when we get over to this block of elements over here, we have row or column 13, which actually only has 3 electrons in the outermost shell of those atoms. Notice that the older numbering system, 3A, 4A, 5A, 6A, 7A, is simply the newer numbering system, minus 10, because there are 10 columns in here between columns 1, 2, 13, 14, 15, 16, 17, and 18. Using that logic, if we look at fluorine, we would imagine that if this system is working, that there would be 7 electrons in the second row. So there are 9 total electrons in fluorine. The first 2 go in the shell closest to the nucleus, and so there's 7 left over, and I can put up to 8 in the second shell, so I can put all 7 in the second shell. So in fact, fluorine, which is in row 2, has electrons in the second shell, and there are 7 electrons in that second shell, corresponding to 17 minus 10, or 7A. The outermost electrons are called the valence electrons. It turns out that the valence electrons are the ones that dictate the properties of an element. And so, as it turns out, all the elements in a given column have the same number of valence electrons, and so they share common properties. Elements in a given group or column are given a particular name. So we refer to column 1 elements as alkali metals, column 2 as alkaline earth metals, and we refer to the elements in column 16 as the chalcogens. Column 17 are the halogens, and column 18 are the noble gases. All of these elements in here, in these 10 columns, are called the transition metals. Notice that most of the elements in the periodic table are metals. In fact, we can draw a dividing line in the periodic table right about here. And all of the elements on the left-hand side of that dividing line are metals, and the elements on the other side of that dividing line are nonmetals. That's going to become important because metals and nonmetals behave very differently.